In this final video on hypothesis testing, we will be covering 2 more hypotheses tests. By now, after watching the previous 2 videos, you should be clear on the 6 steps in hypothesis testing, as well as the rejection criteria of the null hypothesis. So let's dive into the 2 tests that we'll be covering: the paired t-test and the 2-sample t-test. They may seem very similar, but they have very different applications, and it's important to understand how to identify which one to use and how to use it. Let's look at the paired t-test first. The paired t-test is used only for 2 samples that are paired by nature or construction. The 2 samples should be nearly identical at the start of the experiment. For example, if we wanted to investigate a new diet, we would take measurements of each subject before they went on the diet and after they went on the diet, and make a comparison on each subject's differences. We would not compare a new set of subjects on the diet with the original subjects tested. We could, however, test an identical set of twins in a different manner. We could test a diet on one of the twins and compare the data on the twin that was not on the diet, as we would assume that they are identical in every aspect, and therefore they can be compared without affecting the independence of the test. You will also notice that both samples of data need to be of the same size. The hypothesis for the paired t-test is as follows. The null hypothesis states that the mean of the differences is 0. In other words, there is no difference, while the alternative hypothesis states that the mean of the differences is not 0, and therefore there is evidence that there is a difference in the 2 means. Next, the assumptions to check are based on the difference between the 2 sample means. First, we need to confirm that the differences are independent. In other words, there aren't several other factors that are creating a difference between the 2 samples being investigated. Second, we need to check that the differences between all the observations are normally distributed. This can be checked by using the central limit theorem if the number of differences is greater than or equal to 25, or by plotting the differences in a histogram to check for a bell-shaped curve. Now let's look at the 2-sample t-test. We can use the 2-sample t-test on 2 different populations. For example, we could compare the weights of subjects on diet 1 with the subjects on diet 2. We don't need the 2 populations to be identical. We could also compare the average heart rate of males to the average heart rate of females. We can also have different sample sizes for the 2 samples. The hypothesis for the 2-sample t-test is as follows. The null hypothesis states that the mean of the population 1 is equal to the mean of population 2, or in other words, that there is no difference in the means, while the alternative hypothesis states that the 2 populations are not equal, or that there is evidence that the population means are different. Next, the assumptions of the 2-sample t-test requires that the 2 samples are independent. In other words, there is no relationship between the 2 samples. Secondly, both samples' data are normally distributed. This can be done by once again looking at the histograms of both samples, or we can check if each of the sample sizes are large enough, and therefore we can use the central limit theorem to state that the sample means are approximately normally distributed. Finally, we need to check that the standard deviations or variances for both populations are the same. This can be done by looking at the box plots of the samples. We can investigate if the sample spread seems approximately the same for each of the samples. This will then allow us to state that the standard deviations or variances are approximately equal. For example, the yellow, blue, and red box plots are nearly the same length. However, the green box plot is clearly much smaller. Hence, we can assume equal variances for the samples that are from the yellow, red, and blue box plot, but not the green box plot. It may still seem difficult to choose between the 2 tests. However, choosing the correct test will be easy if you understand the case study and research question. Are there two populations that are being compared, or is it one population? Do the sample sizes vary, or are they the same? Identifying the correct test will become clearer once we look at some examples. Let's begin looking at some worked examples. Here is a case study. A study was conducted on the effect of a new training regime on the IQ of 26 subjects. The 26 subjects' IQs were tested before the training and after the training. Our research question is there a difference in the subjects' IQs after the training? Here is the IQ of the 26 subjects before the training, labeled IQ1, and their IQ after the training, labeled IQ2. So now, which hypothesis test should we use? Paired t-test or two-sample t-test? Well, let's re-look at the case study again. We have the IQ of the 26 subjects before and after training. Recall that paired t-tests are used for before and after data samples. We also have the same sample size for the before data and the after data. The same sample of people were used for the first IQ test and for the second IQ test. It's clear that we can use a paired t-test. We can now work out the difference between the first and second IQ test scores and begin the 6 steps of a hypothesis test. First, let's state the hypothesis. The null hypothesis states that the mean of the differences is 0, while the alternative hypothesis states that the mean of the differences is not 0, and therefore there is evidence that there is a difference in the subject's IQs before and after training. Next, the assumptions. For the first assumption, we can assume that the differences are independent, as the same sample of people were tested before and after training. Second, we need to check that the differences between all the observations are normally distributed. As the sample size of the differences is also 26, we can use the central limit theorem. However, I've also added the histogram of the differences, and we can see that the differences does have a bell-shaped curve. Hence, we have confirmed all the assumptions and may continue with the hypothesis test. Let's move on to calculating the test statistic. The test statistic is the mean of the sample's differences minus the predicted mean of the differences divided by the quotient of the standard deviation of the sample's differences and the square root of the sample size. We also need to take into account the degrees of freedom, which also happens to be the sample size n minus 1. The required statistics can be found using Excel and the provided data. Here's the output of the descriptive statistics. We can find the mean of the differences, which is 4.577. Then the standard deviation, which is 2.062. Now we're ready to calculate the test statistic. The test statistic is 11.3154 with 25 degrees of freedom. We then can calculate the p-value, which we find to be very small. We use the same function in Excel as we would to find the p-value in a one-sample t-test. As the p-value is very small, we note that it is less than 0.05. There is also an alternative method to calculating the test statistic and p-value when you have the dataset. You can use the data analysis tool in Excel and use the paired t-test option available. This method is quite efficient. Here is the output. You can see that we can find the test statistic and the p-value in the table. Note that we use the two-tail p-value for the paired t-test. Also, the test statistic here is negative 11.3154. This difference is caused by how the differences of the two samples were calculated. However, it does not affect the overall outcome of the test, as we use the absolute value of the test statistic to calculate the p-value. Note that the absolute value of a number is the size of the number and therefore ignores a positive or negative sign on it. Next, we are ready to make a decision. Given that our p-value is less than 0.05, we can reject the null hypothesis in favor of the alternative hypothesis. Finally, we state the conclusion. We can conclude that there is evidence of a significant difference in the IQ scores before and after training. On average, the IQ scores after training had increased. Here is another case study. A study is being conducted to investigate 2 greenhouses that are growing cucumbers. The weights of 28 cucumbers from greenhouse 1 was taken, and the weights of 26 cucumbers from greenhouse 2 were taken. The research question is there a difference in the average weight of the cucumbers harvested from greenhouse 1 and 2? Here's the data collected from the 2 greenhouses. Now, which hypothesis test should we choose? Paired t-test or 2-sample t-test? Let's look at the case study again. We have data collected from 2 different greenhouses. The sample sizes for the 2 greenhouses are different. Hence, it would be best to use a 2-sample t-test. We can now begin the hypothesis test by stating the hypothesis. The null hypothesis states that the mean weight of greenhouse 1's cucumbers is equal to the mean weight of greenhouse 2's cucumbers, or in other words, that there is no difference in the means. While the alternative hypothesis states that the mean weights of the cucumbers from the 2 greenhouses are not equal, and hence there is evidence that the mean weights of the cucumbers from the 2 greenhouses are different. Next, we can check the assumptions. Firstly, the 2 samples seem to be independent. Secondly, we can check the normality by looking at the histograms of both samples, which both have a bell-shaped curve. However, as we do know that the sample size of greenhouse 1 is 28 and greenhouse 2 is 26, we could have used the central limit theorem to state that the sample means are approximately normally distributed. And finally, we can look at the box plots of the samples. The spread of both box plots seems similar. Therefore, we can assume that the standard deviations or variances are approximately equal. It's time to calculate the test statistic. The test statistic is calculated as follows, with degrees of freedom calculated by adding the sample size of the first sample and the sample size of the second sample, then minus 2. We also need to calculate a pooled standard deviation, denoted as SP. The pooled standard deviation can be calculated by first calculating the pooled variance, denoted as SP squared. It requires the variances of the 2 samples. To get the necessary statistics required, we can use Excel. We can find the mean weight of cucumbers for greenhouse 1, the mean weight of cucumbers for greenhouse 2, and their variances. Now we can calculate the pooled variance, which we find to be 0.663713. Then take the square root to find the pooled standard deviation. Next, we can calculate the test statistic, which we find to be negative 2.03261. We can now calculate the p-value, which we will calculate using the same function in Excel, which gives us a p-value of 0.047042. This p-value is just less than 0.05. The alternative method to calculate the test statistic and p-value would be to use the data analysis tool with a 2-sample with equal variances test, which would give us the following output. As you can see, the test statistic and p-value is the same as the one we just calculated. Additionally, you can find the pool variance here, denoted SP squared. To find the pooled standard deviation, you would just take the square root of the pooled variance. This will give us SP, just as we calculated earlier. Note that it wouldn't be possible to create this Excel output or use this method if you do not have the sample data. Next, we are ready to make a decision. Once again, given that our p-value is less than 0.05, we can reject the null hypothesis in favor of the alternative hypothesis. And finally, we state the conclusion. There is evidence of a significant difference in the average weight of cucumbers produced in the two greenhouses. On average, the weights of the cucumbers from greenhouse 2 are more than those from greenhouse 1. We've finally reached the end, and it's time for a brief recap of what we've learned. We know how to state the hypotheses for the paired t-test and the two-sample t-test. We also know the assumptions for both tests. We can check for normality using a histogram, or we can use the central limit theorem when we have a large enough sample size. We can check for equal variances or standard deviation using box plots. We also know that the paired t-test is used for two samples that are paired by nature or construction, and that they should be nearly identical initially. It's also important that the sample sizes are the same. For the two-sample t-test, we can compare two different unidentical populations. We can also have different sample sizes of the two populations. However, it is important to remember that it is possible to use a two-sample t-test with two samples of the same size. I hope these videos have helped you to understand hypothesis testing, and especially which tests to use.